Welcome guys to today's class. In today's video, we want to discuss an important topic called optical activity. Yes. So we want to understand the concept of it and see how we can solve some problems on it, like this one we have on the board. So let's start with definition. Optical activity is the rotation of the plane of polarization of linearly polarized light as it travels through a certain materials. Let's take it again. Optical activity is the rotation of the plane of polarization of linearly polarized light as it travels through a certain material. You will understand it more as we continue this class. This term, optical activity, can be called optical rotation or rotary polarization. Now, for a molecule, for a substance, for a drug, for anything to be called an optically active substance, it means that it has chiral centers. What do we mean by chiral centers? Let's take an example. One of the molecule or one of the substance that is optically active is what you know, glucose. Yes. Look at this glucose. This glucose can be called D-glucose, L-glucose. Look at it. D or L-glucose. When do we call a glucose D-glucose? When do we call a glucose L-glucose? Let's see from the structure. Let's check the simplest structure of it. Okay, glucose has 6 carbon. 1, 2, 3, 4, 5, 6. We call it D-glucose because of what happened at carbon 3 here. If you start from here, 1, 2, 3 at carbon 3. You notice that hydrogen is at the right while OH is at the left, looking at it this way, right? That means this is called D-glucose. You call it L-glucose if this thing you are seeing here interchange. Are you getting it? If it's interchange so that this goes here and this come here, you call it what? L-glucose. How do we mean? D-glucose is called dextrorotatory glucose. L-glucose is levo rotatory glucose. That means when a plane polarized light goes through this glucose molecule has what it takes to rotate it to the what? Right. That is for D-glucose. It has what it takes to rotate it to the right. We call it D-glucose. But if it rotates it to the left, you call it levo glucose. That is L-glucose. You see, why do we say that it has the tendency to rotate a light ray? Yes, it has the tendency. Let's see how. We could talk about chiral centers, that every molecule that has the tendency to rotate light ray, it must have what? Chiral centers. What do we mean by chiral center? Chiral center is an atom in a molecule. It's an atom in a molecule that is bonded to 4 different chemical species. When you have an atom in a molecule bonded to 4 different chemical species, we call that molecule that it has chiral centers, so to speak. If it has one chiral center, you say it has a chiral center. If it has more than one, you say it has chiral centers. Let's know. Glucose is noted to have 4 chiral centers. How? This first carbon, because it's an aldehyde group, we start from the aldehyde group. So at this first carbon, we now say how many chemical species bonded to it. This is 1, this is 2, and this is 3. So it's bonded by 3 chemical species. But what we are looking at is 4 chemical species bonded to an atom in a molecule. And so we say this is not a chiral center. It's not a chiral center. We come here, this is bonded to this. You see the name of the molecule, aldehyde group. This is a molecule hydroxyl group. This is a molecule hydrogen atom. This is a molecule, another name, bonded to what? Carbon, right? That means there are 4 different chemical species bonded to this carbon. We call here a chiral center for this glucose, right? We check this one. All these are bonded to this, they have their name. This one, they have its name, hydrogen. This one, OH. This one have its own name, and they are different. This is different from this, is different from this, is different from this. And so we say that this one have a chiral center. This is a chiral center too, the second chiral center. We'll come to this. This have its name, this have its name, you get? They are different. This have its name hydroxyl, this have its name. So 4 different chemical species bonded to carbon. Third chiral center. This one, all this bond to this bond to this bond to this, and there are 4 different chemical species. We say this one also have chiral center, and that is why we say glucose units, whether L or D glucose units, have 4 chiral centers. Yes, take note. I believe you understand what I just said now. If there is anything you do not understand, please feel free to what? Use the comment box below and what? In your view. So what we are saying is that glucose has what it takes to rotate light rays. Yes, it has what it takes to rotate light rays, either to the left or to the right. And that is why we say glucose unit, glucose molecule is an optically active molecule or substance. Yes. Now, it is important to note that there are other molecules, other substances that are optically active, such as drugs. Yes, some of the drugs we have today are optically active. Take note. Proteins, sugars, they are optically active. So have it in your mind as we discuss more on this. Now, if you want to measure how optically active a particular molecule is, there is an instrument that is best used to do that. We call it polarimeter. Polarimeter. This is an instrument that we use to what? Check how optically active a molecule is, a substance is. Yes. So have it in your mind that if you want to check how optically active a molecule is, you go and look for polarimeter. We would have discussed more concept of this, but because time, let's just run down main points we want to talk. Now, optically activity of a molecule or drugs or substance or sugar whatsoever depends on several factors. That means if you want to know how optically active a particular molecule is, a particular substance is, there are factors it depends on. 1 is temperature, 2 wavelength, 3 path length, and 4 the substance being involved, the substance you are analyzing, the nature of the substance, so to speak. Yes, even the concentration of that substance is also involved. Yes, and so these are the factors that can affect how optically active a particular molecule is. Let's see some formula you need to know when you want to do some calculation on optical activity of a molecule. Let's see. Observed rotation denoted this way, alpha OBS, observed rotation, is equals to specific rotation denoted this way times length times density for pure liquid. If you are talking about pure liquid, look at the formula. Now, it is important to note that when sodium D line is used, when sodium D line is used, this symbol will be replaced with. That means when you see this symbol in your textbook, it means that sodium D line is used. So have to know this. Okay? Then observed rotation for solution is equals to T over D if sodium D line is not used times length times what? Concentration. Note that concentration can be in gram per mil or gram per what cm cube. Concentration and density can be in gram per mil or gram per cm cube, because 1 mil is equivalent to 1 cm cube. So whether concentration, whether density, look at their unit. The length can be in dm or equivalent to what? Cm. It can be in dm, it can be in cm, but note that the best unit used to measure this length is in dm. That means 1 dm is equals to what? 10 cm. Okay, so there is need for you to know what these parameters mean. This is observed rotation, this is the specific rotation, this is the length, and this is the density. This is observed rotation, specific rotation, length, and concentration. Yes, so you have to note this. Now if you are looking for unit of this, very important, you know, in science, unit of what you just solved is very, very important. And so this specific rotation can be, or the unit is, from observed rotation all over length times concentration or length times density. This observed rotation is measured in degrees, so the unit will be in degrees, right? This length, if it is in dm, you bring it up per dm. This concentration, gram per what? If it is gram per mil, it means that the mil will come up, then the gram will have inverse. Or if the length is in centimeter and the concentration is in gram per centimeter cube, you notice that here is centimeter times gram per centimeter cube. This will cancel this, making it centimeter square, right? And so you will be having it that degree, this come up per gram, then centimeter square. Yes. Then if the length is in dm and this is gram per centimeter cube, you'll be having the unit to be degree. This is in dm per dm, then centimeter cube. All this depends on what you use. This in dm, that is why you are using this unit, and this is gram per what? Cm cube. Then this is in degree. Then this one is when you use LO to be in dm, and this concentration gram per mil, you make sure that the unit goes this way. Okay, let's see how to solve this question. A sample of pure S enantiomer of a drug was placed in a 10 cm polarimeter tube. Using the D-line of a sodium lamp, the observed rotation at 20 degrees Celsius is C, while we say temperature is involved. Was observed rotation is this degrees. The density of this compound is 0.805 gram per mil. What is the specific rotation of the compound? Wow. To solve this, the specific rotation, which is this, is equal to observed rotation given to us is 104 degrees all over this is the length in 10 cm. If I want to use it to be in dm, I'll just say dm. This is equivalent to 1 dm. 10 cm is in 1 dm. I've converted it to dm. If I want to leave it as cm, I can use it. I just put 10 cm times concentration gram per mil. That means I will be using, I will know that the units will now change. I will know that the units will now change to degree. If I'm using this cm and this word, I will know that it is degree per cm, then mil per gram. I will know that this is what it will give me. Yes, yes. And so I want to use it as 1 dm. I will now say 1 dm is that 10 cm you see there. 1 dm times what? 0.805 gram per mil. This will be giving me 104 over 0.805. If you press it in your calculator, 104, this times is 0.805. You press it in your calculator, it will be giving you 129.19. The unit degree, then per dm, then per gram, then mil. Recall, we said the answer is 129.19 degree per dm, because I converted to dm, then per gram, then mil. That means I am following this unit. So that is the answer to that question. Thanks for watching today's video. So please feel free to share this video to your friends, to your classmates. Wish you success to your exam.